Hi, my name is Mark Davidson from DreamVu. Thanks for joining today's Tech Talk. We're going to be talking about selection criteria for an industrial grade 3D vision system for AMR obstacle detection. Now, this Tech Talk, it's about 20 minutes, is going to give a lot of insight into what we believe to be very important criteria and how different sensors stack up against that criteria. You'll be able to download a white paper that not only covers the material of the white paper of the presentation, but a lot more additional detail, more criteria and more detail for each criteria. So today's agenda, an introduction to the selection criteria. We're going to compare some of the most critical criteria. And then again, you'll have an opportunity to learn about the white paper that's available for download. Two main sensors we're going to be comparing today, what we call PAL from DreamVu. It's a 360-degree stereo depth camera. And Intel Realsens D435, a very popular stereo camera that we see used frequently. So as you'll see in the white paper, there are 22 critical criteria that we consider. And many of those will be covered today. You can see a bunch of the criteria below on the agenda. So again, not going to cover it all in this Tech Talk, but in the white paper, you'll be able to see it all. So the first one is range and depth accuracy. Now let's define these two things. Detection range, the range with which an obstacle can be detected. So let's say detection range of 10 meters. What that spec means that anything within a 10-meter radius from the sensor will be detected. Depth accuracy is the range with which the accuracy of the depth information is usable. So while something might be detected to 10 meters, the accuracy at 10 meters might not be very good. So the depth accuracy range, maybe it's 5 meters or 7 meters, something along. So detection range, how far to see it. And then depth accuracy is the range where we believe the depth accuracy is usable. Field of view is another one. And here's an example of PAL, 360-degree horizontal field of view, 110-degree vertical field of view. And of course, we at DreamVu believe that the larger the field of view, the better. Now for PAL, although it has full 360-degree, you don't have to use all 360-degree horizontal field of view. As a matter of fact, very often there's occlusions created by the robot. Maybe you can only use 220 degrees, 260 degrees, whatever. So the camera provides 360, you can use less than that. Let's talk about lighting conditions. How does it perform in bright or low ambient lighting? Now in this example here, this is the Intel Realsens D435. And what you see on the left set of images and the right set of images is even in dark, the depth performance is the same. Now, Intel uses active projection. That's how they're able to have good operation in low lighting. What you would notice though is beyond 5 meters or so, there's no depth information in either high ambient light or low ambient light. That's one of the shortcomings is while the depth accuracy looks good in both lighting conditions, it doesn't have a lot of depth range. And that's one of the shortcomings we have found in the D435. For comparison, here's PAL. And what you'll see in the top is low light and the bottom is bright light. And what you'll see is not only does the depth information look the same with or without bright ambient lighting, but you're also seeing much more depth range, which is one of the benefits of PAL. What's really amazing about PAL, this is a purely passive sensor. There's no active projection. And because of the construction of PAL, we're able to capture a lot of light even in low ambient conditions. And that's how this thing's able to perform well in low lighting. Here's another example of PAL, not only working in very dark situation, it's outdoor now. That person is detected very clearly. And then again, it's a good example of being able to see a much longer depth range. Again, passive CMOS sensor in dark. Earlier on, I mentioned about how the Realsens product really kind of breaks down at about 5 meters or beyond. And on the left is PAL with the RGB and the depth map. And on the right is Intel Realsens. And what you'll see is as this person goes to about 5 meters, they disappear from the depth map in the Realsens. But with PAL, that person is still detected. Again, really highlighting the depth range. And in this case, is the criteria is about detecting human-sized objects at these various depth ranges. This is highly reflective environments. This is something that's very important, especially for, we see customers building autonomous machines for, let's say, floor scrubbing, commercial cleaning. In the Realsens example that we're looking at here, you see these black spots, holes, and based on where the light is reflecting off of the highly reflective floor. That's a problem. And those holes would confuse the AMR, the navigation system. And the robot would try to navigate around those holes, but the fact is they're just reflections. Now here's an example, very similar setting. You see the bright light reflecting on the floor here, and this is with PAL and no holes, which means now the AMR is going to be able to navigate and maneuver much more efficiently. So how it performs in highly reflective environments is important. Also detecting non-reflective obstacles. Again, here is Intel Realsens. And what you see is the inconsistency in the depth map of these non-reflective obstacles that are detected. And that inconsistency of depth shown by the different colors, that could be confusing to the AMR navigation system. So we want to make sure that when detecting non-reflective obstacles, and again, with the Realsens active projection, sometimes that active IR gets absorbed by the non-reflective. And similar, here's PAL. Again, same non-reflective obstacles, the white one on the left, the black one on the right. And I put blue ovals because they kind of blend in. And what you see is nice, consistent depth map on the obstacles, shows the reliability and robustness. And then, of course, being able to detect any and all obstacles anywhere around, within the field of view, anywhere around the AMR. So what you see here is all the obstacles that are spread across the floor, and of course this is 360 degrees, are detected. And what you see is this green laser. Now, although our camera does obstacle detection using the full vertical field of view, what we do, and we'll talk about this in a couple minutes, but we flatten it into a 2D laser scan to reduce the amount of data bandwidth required and memory required to take advantage of the large field of view obstacle detection. Other criteria, what AMR speed can be supported? There's really two critical parameters here. One is frame rate. We're looking for greater than 20 frames per second or 20 hertz should be considered for a standard indoor AMR. And latency, and of course latency is how long it takes the data to be processed and available for the navigation system to use. And we're saying less than 150 milliseconds is a criteria. The white paper will dig into this a lot more with a lot more detail. So those are two important parameters that will impact the speed with which the AMR can operate. Floor mapping. This is something that we see a lot of customers asking for. It's a goal that is not often accomplished, but here's what PAL is providing. And the blue is very clearly the floor map. And very important because when we know something is on the floor, we see the plane of the floor, means everything else above that is an obstacle. So it really helps improve depth accuracy and obstacle detection. Ignoring false positives. What we see here, we put some green tape on this highly reflective floor. And as the green laser shows, that green tape is not detected as an obstacle. That's the goal. And it shows the robustness. And again, this is PAL. It shows the robustness of the obstacle detection and floor mapping algorithms that are so important. So we want to make sure that we ignore false positives. Data bandwidth, as I mentioned before, it's very important. The more data that the sensor captures, of course, you got to transmit that data, you got to store that data, you got to process that data. It does affect latency. So as I mentioned, what we do is we do 3D obstacle detection, but then we flatten into this 2D plane. So now we're compatible with any, let's say, G mapping, any of the 2D mapping solutions that are prevalent in most of our customers' navigation systems. And what this maybe doesn't do a great job of showing, whether the obstacle is on the ground or hanging and not touching the ground, they're detected and flatten into that obstacle, into the laser scan showing the obstacle map. Software compatibility and support. You want to make sure that, and this is probably an area of concern with some of the decisions Intel has made with the Realsens product line. what is the support? What is the ongoing compatibility? So you want to check and make sure that that there's a robust selection of APIs. Of course, ROS, different architectures. We see NVIDIA and ARM very, very popular, but we also see people using x86, Intel NUC, those sorts of things. So you want to make sure that the environment to evaluate, develop, and qualify is important, and you want to make sure it's well supported. So I flew that very quickly with the goal of trying to get some Q&A time in this short tech talk. But as I said, there is a white paper available that's going to give you a lot more criteria and a lot more detail for each of the criteria. So be sure to download it. You can download it directly from Vision Systems Design, or it's also available on the DreamVu website. Either way, it's available to you. I like to end every one of my talks with why field of view matters, because what we do see is a lot of sensors out there that are very, very good, but with a narrow field of view, be it a 2D LiDAR that doesn't give you great vertical, or traditional stereo cameras that have narrow horizontal and vertical field of view. So why does field of view matter? Improve maneuverability, increase runtime, because we're not stitching many sensors together, and it reserves the compute resources for other value-added functions, such as object recognition, driving latency down so that you can run your AMR faster, et cetera. Sensor fusion is computationally intense. Fewer sensors reduces the burden. So if you're interested in getting started with any of the DreamVu technology, we have starter kits, PAL starter kit, PAL mini starter kit. Those are two of our most popular cameras. And then obstacle detection solution starter kit. This is one where you plug it into, you need a keyboard, a mouse, and a display. And within a couple minutes, you're observing and evaluating the obstacle detection solution. So feel free to go to our website. You can buy starter kits. And as a reward for listening to this tech talk, we do have some discount codes for you. So PAL mini starter kit or PAL starter kit. Either one will save you some money when you go to buy a starter kit. So thank you. I went very fast, and now we'd like to have a question and answer session. Thanks again for listening.